Hello. Oh,
Oh. Could have been doing that the whole time.
could have been doing what?
It's full screen.
That's what I did last time too.
But you had the.
Did I?
Oh, it did. Yeah, never mind. I thought it was without the. It doesn't matter.
Yeah. Okay. Hi. This is a tutoring example that I'm doing for a learner, and this is my pretend student for the day, Gary. We're going to be doing 2 math problems. So, it's been a long day for both of us, so we might be a little bit, but that's okay. You got to deal with students after school when they're tired, so it's good practice. Okay, so we have 2 problems. One's a word problem, one is a more straightforwardly notated, just a math problem. We're going to start with the word problem. So the cost of gas increased by 10 cents this week. Last week, a man bought 20 gallons at the old price, and this week he bought 10 gallons at the new price. Altogether, the cost of gas was $61. What was the old price for 1 gallon? Okay, so the way I like to break these problems down is by going first through what are the pieces of information, the things we know and the things we don't know that are given to us by the problem text. So, Gary, let's go through, and can you point out to me what are our knowns and unknowns?
The increase of price, cost.
Yeah.
20 gallons.
Yes, at the old price.
10 gallons at the new price.
Mm-hmm.
$61 altogether.
Altogether.
That's it.
And then we want the question. The question is, I can do a different color actually. That's what we're looking for. The thing we're looking for is the old price at 1 gallon. So we are solving for what is the old price for 1 gallon of gas. What is that? That's what we're looking for, and we're going to give it a shorthand name in a second. So we're also looking for, are we looking for the new price? No. We're
Well,
not.
the question only asks
For
for
the old price. Exactly, but we have a price increase. So from the old price to the new price, there is this increase of 10 cents. So that's important to know. And then we also wrote down that in the first week, we bought 10 gallons at the old price. And then on the second week, we bought 20 gallons at the new price. And we had a total cost of $61. So one way of saying that is that the cost for the first week let me redo that, sorry. The total cost what would you, so there's the price of the gas. We're getting at like the expenses, the total expense. So maybe that's a more helpful word. So the expenses for week 1, I'm going to do a subscript for week 1, and the expenses for week 2, total $61 altogether. And then we need to find a way to represent expenses. And in particular, we know that we get a total expense both from a unit cost and also from the number of gallons that we buy. So we buy, which means that if I buy 10 gallons of gas, I have to pay a certain price, certain number of dollars per gallon of gas.
Mm-hmm.
So that's going to look like on paper. 20, well, he said 10. Yeah, let's say 10. Our example is 10 gallons of gas. And then multiplied by the unit cost
Mm-hmm.
by some amount. Let's say $3 per gallon. $3 per gallon of gas will give us a total expense of, what do we have to do?
Multiply them, so 30.
Yeah, 30. And the important thing is these two units cancel. The gallons cancel out. So we get $30 worth of gas. Boom. So we can take this example and abstract it out and then plug it into our last equation.
Mm-hmm.
And in particular, we know, so do you know what I'm talking about when I say unit cost?
The cost of one unit.
Yeah, or yeah. So what am I meaning? What do I mean when I say unit?
A gallon.
Yes, here specifically. Yeah. So there's some quantity that we're measuring. In this case, we're measuring gallons of gas, and then there's some conversion rate that we have to turn gallons into a dollar expense. And that is like our unit cost. And so in particular, so here we use specific numbers. We use 10 gallons and $3 to get $30 total. But we could also just write gallons times dollars per gallon is equal just to total dollars, something like that. And the notation is a little funky there, but there is, so just full disclosure, this is our second run through, and I'm trying to remember, there's some stuff from the first run through that may or may not want to bring in. But an important thing to look at is that the idea here, so there's focusing on this unit cost again.
Mm-hmm.
Something important about it is that it's a fraction.
Yeah.
So it's in the numerator we have dollars over gallons, and here's the thing. In our equation before,
Mm-hmm.
we have one example, because there's a couple different unit costs in this problem, and one example that we can find is we had $61 in total expenses for 30 gallons of gas over 2 weeks, and that's a fraction
Mm-hmm.
that can turn into a unit cost, but it's not a unit cost yet because we haven't when we talk about something per 1 gallon per gallon, we've like normalized it. So we need to simplify this.
Mm-hmm.
We can divide by 30 here, take that out of the numerator and divide by 30 on the top, and we're gonna have about $2 per 1 gallon, and that is a unit cost. But the important thing is to note that in order to go from one quantity to another quantity where the units are different, we have to have a ratio, a fraction of the two, that lets us sort of translate the quantities. So finally coming back to this equation right here, we have expenses, and we know that a total expense, because an expense is a conversion of a quantity of gallons to a quantity of dollars, we know that one of these expenses is going to be represented by the unit cost from the first week, and then the quantity of the gallons from the first week, and then the same thing over here. We have the costs from the second week and the gallons from the second week. And so that's almost enough now to solve the whole problem, because we have most of the pieces of information so that we can just plug them in. But it's important to remember, what is it that we're solving for again?
Old price.
Old price. So yeah, so where it gets interesting is we are looking for old price. In this case is the unit cost from the first week. So we actually don't know what it is. And if we look at our knowns and unknowns, we don't actually know. We know the difference, the 10-cent difference between the old price and the new price. We don't actually know either the old price or the new price. All we know is the difference and ultimately what we paid, the $61. But at this point, it's good to take the information that we do have and start just plugging it into this equation that we've made. So I'm going to write it out one more time, but now really abbreviated. So I'm going to have the first week's cost times the first week's quantity of gas plus the second week's cost and the second week's quantity of gas, and then I'm going to have the total expense across both weeks. And we know that the first week we spent we bought 10 gallons. And the second week we bought, what did we buy?
20 gallons.
20 gallons. And here's something. In this problem, so we're only solving for one variable, this problem, right? But how many variables do we have in this equation? Two. So we have C1 and we have C2. The original cost, the old cost, and then the new cost, the new price. We can solve for the new price, but we don't need to solve for the new price. And to solve this particular equation, we can only solve the equation if there's one unknown, because it's just one equation. So is there a way that we can get rid of C2?
We put it in terms of C1?
Yeah, and we're able to do that. And we're only able to do that because we were given at the beginning of this problem the information that we can turn any given old price into a new price if we increment the old price by 10 cents. So another way of saying that, going back down here, is that the new price is equal to the old price plus 10 cents. And now we have a single variable directly in terms of another variable, which means that now we can just substitute it into our original equation, which will make us, what's that going to look like?
C1 times 10 gallons.
Yeah.
I think you're missing a plus there in your equation up there.
Oh, thank you. Thank you.
Plus C1 plus 10 cents times 20 gallons.
Yes, so we just, when we substitute, it's always good to keep things neat,
Mm-hmm.
to put everything in parentheses, the term that you're substituting in parentheses. So like you said, C1 plus 10 cents and 20 equals 61. And that goes there. And now what do we do?
Simplify.
Right. And the easiest way to do that is to, do you know PEMDAS?
Mm-hmm.
Do you remember what the P is?
Parentheses.
Yeah. So order of operations. You don't. I don't want to say you don't have to follow PEMDAS, but in this case, in terms of simplifying this down to solve it, yeah. The easiest thing to do is you go to these parentheses. It tells you start here. Inside the parentheses, there's not a lot you can do.
Mm-hmm.
C1 plus 10 cents. That's already simplified. But we can take our outer 20 and distribute it over the two terms inside of the parentheses. And so we're going to get, what are we going to get?
C1 times 10.
Times 10? Yeah.
Starting,
yeah.
are we just doing the brackets?
Just tell me the brackets.
C1 times 20,
Mm-hmm.
or 20C1.
20C1. And that's the thing. If I had written things a little differently, I would have put the
Mhm.
10 before the C1 earlier, because it's good to have numeric constants ahead of variable constants. But yeah, so 20C1, and then plus
$2?
$2, and just to make it very explicit for people following at home, we can do it as 20 times 10 cents, and that's going to simplify to an easy way of doing it is 10 cents means that in the multiplication that we do, we're gonna move that decimal place on the 20 over once,
Mm-hmm.
like that, and so we're gonna get $2. Then over here plus 20 C1, and that's the end of the distribution of the brackets. Then over here, what do we have? We have the
10C1.
10C1. We can rearrange those just to make things a little bit easier. And why can we rearrange them?
Because it doesn't matter what order you multiply them in?
Yes, it's a commutative operation, which is a good thing to always know about. $61 on the right. And now we're at a point where, because we've completely simplified what's inside the brackets and there's no more things to multiply by outside the brackets, we can get rid of the brackets. You know, we can start combining like terms. And in this case, are there any like terms for this 2 here on the left side? No, so we can leave that alone. But there are like terms in the sense that we have two sets of terms with C1 in them, so we can put those together. So 10 C1 plus 20 C1, what is that?
30 C1.
30 C1, yep. And then bring this 2 down, plus $2 equals $61. What are our last 2 steps?
Move the 2 over.
Yep. Over. And final step.
Divide by 30.
Divide by 30. And yeah, so depending on who your teacher is, some teachers would let you leave it just like this, as 59/30ths of a dollar, because it's a little messy to calculate that yourself. Most teachers probably want you to give an exact dollar amount. We know, because 59 is very close to 60, that in terms of checking our answer later, our answer is going to be very close to $2. But because 59 is less than 60, what do we know?
It's gonna be less than $2.
Exactly. So our actual answer will be slightly less than $2. And I'm gonna guess off the top of my head that it's $1.95
Okay.
because we did this yesterday, but I don't actually remember. So now here's the part where I am most rusty, which is the simple arithmetic. The 59 and 30. There's a trick you can do, which you don't have to do. But if you want, dividing by 30 is kind of intimidating because it's a 2-digit number.
Mm-hmm.
But if we wanted, we could get rid of that 0 as long as we also divided 59. So 30 divided by 10 is 3. 59 divided by 10 is 5.9. And all that is I moved over my decimal point by 1 place. And then that point goes up here to the top like this. You just have to not lose track of it up there. And then 3 goes into 5 how many times? 1 time, 1 times 3, 2, 9. And then 3 goes into 29.
9 times.
Yes. 27. Oop. Touchscreen being a little funky. 0, 2. So I need to make a placeholder 0. Oh, it's not 95. It's gonna be a
Yeah, it's 6.
Yes. 6. And it's gonna be just by looking at this already, 3 never divides nicely into 20.
Yeah.
So it's gonna be 6 repeating forever. 6, 6, 6, 6, 6. Which means that for the purposes of getting an answer that's nicely rounded, we can round 666 rounds up to 7 exactly. So not quite $1.95, but we're gonna get in the end the old cost is still only about $1.97. It's exactly $1.97 in the sense that in terms of significant figures, we've done our job. In terms of like the absolute answer, just math-wise, it's approximately. So now the last step I would want to do is plug some of this back in to make sure that our answer makes sense. Okay. Just knowing about gas prices every day, like when you go to the pump, just $2. It's a little bit low, but it's kind of in the ballpark of what you could pay for gas.
Sure.
So it passes.
I wouldn't know if I was in middle school.
Right. Yeah, that's true. But it kind of passes the sanity check. Like it's not. If someone told me you have to pay $100 for gas, either we'd be in a lot of trouble or we got the wrong answer. So passes the sanity check. But the next step is if we need to make sure that this first equation right here, that our answer when plugged into the first equation checks out. And keeping in mind that the C2 term is just C1 plus 10 cents. So do I want to rewrite this or do I want to? It's okay, we can. So I'm going to clean up a little bit, but with a new color, let's do green. So I'm gonna cross out this C1 here, and I'm gonna bring in my $1.97. So my C2, what's my C2?
207.
207, yep. Which means that up here, I'm going to again just substitute in. So cross out C1 and C2, $1.97, $2.07. Now the final step is just to do the arithmetic. Yeah, so $1.97 times 10, what happens?
19.7.
Yeah, so I can just gonna rewrite it this way. So 1.97 times 10 means since we're multiplying by 10, we're getting a bigger number, which means we're gonna move the decimal point to the right. So 19.7, and then 207 times 20 is a little bit more complicated. You can do it in your head probably, but I would say for people who can't, what I would like to do is you can say 207 times 10, but then times 2. So that way you keep the ease of just moving the decimal point and then you double it afterward. And that's the same thing as multiplying by 20. And that time it's because of something called the associative property, which says the order in which we do stuff is up to us. Okay, so 207 times 10 is
20.7.
20.7 because we move the decimal. And then 20.7 times 2.
41.4.
Slightly messy because you have to carry a 1, but 40 and a bit, so 41.4, 0, just because we're talking in cents. So then to rewrite it all more cleanly over here, we have $1.97, sorry, $19, thank you, $19.70 plus $41.40 should be, if we've done our job right, approximately $61. And let's see if it is. So 19 and 41 is 60. And then 70 and 40 is $1.10. So $1 plus 60, 61. And then we have 10 cents left over. And so 10 cents is approximately $61. And I will call that good enough. And the reason why there's a discrepancy is, again, because we had to round, because the $.6666666 we have to round. But that's pretty close and good enough. So that's not so bad. And again, do you want to maybe tell me in your own words how we got to where we got?
We made two equations and plugged one into the other.
Yeah. So, and we figured out what those equations needed to be by first parsing the problem. So we found out there was a relative difference in cost, and we also found out there's like a total quantity of a commodity, and then we kind of, using the data that we had, sort of wrote out some generic equations and then plugged in specific values, and like you said, put one cost in terms of the other cost. That led us to the equation plug-in, and then from there we solved. And we checked our work. One thing that we ended up talking a bit about on our first time through this, that you don't directly need to know for solving this problem, but that's really valuable, is the idea of a proportionality constant. In particular, if you go into science courses in high school, like chemistry or physics, you're going to do these things called unit conversions. And we did that when we took a quantity of gallons. So when we had 20 gallons and we needed to turn it into a certain number of dollars that it cost, we used the unit cost to convert those units. And the thing is, that fraction, that ratio that we found, represents a linear relation between gallons and dollars. So 20 gallons times our cost, in this case we could say $2 per gallon. What's really useful here is because the gallons over here, and we could say 20 gallons over 1, which is sort of, gallons is in the numerator, and over here, this is all good. Gallons is in the denominator, those units cancel. And then we end up with an expression where we just have a quantity in terms of dollars. And so by using a proportionality constant, or this unit cost, as we're calling it, we can change units. But more importantly, if you've ever taken algebra, the visual metaphor for this is if you ever graph a line, you have y equals mx plus b. If you forget the b for a second and just think of it as 0, this m is the same thing sort of as our unit cost. It lets us, because if we solve this, we can move the x over here. Y over x is m. This ratio between y and x, which m represents, lets us take any x, any quantity of gallons, and turn it into any y, any quantity of dollars. And so the actual label on the two quantities is gallons, dollars, maybe like feet, Like if you're like the cost per square foot of a house that you're buying, like the labels don't matter, but the important thing is if you ever notice that an expression looks, we call it linear because y equals mx plus b, you can graph it as a line. If the expression looks linear and you can find a proportionality constant, then you can always convert different quantities within that expression using that constant. Which again, you don't need to know that explicitly for this problem, but that is sort of the tool that you're using under the hood, which we talked about on our first run through in a much more roundabout way. So, yeah. Anyway, you feel comfortable moving on to the next problem? Anything else?
Yep.
Okay. Let's check it out. So this one is not a word problem. It is a fun problem, as we found out the long way last time, in the sense that it's not quite a trick question, but it also doesn't give the answer that you might expect. Go down here. Boop. Blow it up a little bit. Okay. So, in some ways this is straightforward, in some ways it isn't. What's it asking?
If 3x minus y is equal to 12, what is the value of 8 to the power of x divided by 2 to the power of y?
So we are given one equation with two variables, 3x minus y equals 12, and then we're given not an equation, but an expression, which is one side of an equation just without the equal sign. And we're asked, what does the expression evaluate to? And most of the time in this sort of situation, because we only have one equation but two variables, we have what we would call two unknowns and just one piece of information relating them, which is not enough to find exact values for each of the unknowns in most cases. This is a really interesting problem because as we're about to see, you actually can find an exact value for the expression 8 to the x over 2 to the y, given the definition of 3x minus y equals 12. But the good news is you don't need to know that going in. You just need to try to solve the problem the usual way and then be pleasantly surprised at the end. So the most important thing is, since the initial sort of thing that should be apparent to us early on is if we have an expression in two variables, it'll make our lives a lot easier. Kind of like in the last problem, we put the new cost in terms of the old cost. If we can put one of these variables in terms of the other variable. And in particular, we'll have to do the least amount of simplification if we put y in terms of 3x, because then we just have to add instead of also dividing. So if I want to solve for y in terms of x, what does that look like?
You move the 3x over to the other side.
Yes. And you can do this two ways. You can,
or you move the y to the other side.
Or you can move the. I like moving. I get tripped up when I have to flip with negative signs. So if we do it your way, we end up with negative y is equal to 12 minus 3x. And then we need to flip this, we multiply both sides by negative 1, flipping the negative, and we get y equals negative 12 plus 3x. In this case, that's pretty easy to do, but if you have a really long expression, sometimes that gets confusing, which is why I prefer to do something like when I have 3x minus y equals 12, I will actually add the y to the 12, and I get 3x equals 12 plus y, and then the last step, since we're solving for y, is you just move that 12 over, and you get 3x minus 12 equals y. Same answer, slightly different way of doing it. Either way, this is important because now we can substitute this expression for y into our bigger overarching expression. So again, that was 8 to the x over 2 to the y. In particular, this y here, can take that, stick it in there, and what's that going to look like?
8 to the x over 2 to the 3x minus 12.
Yes. So keeping the parentheses, 2 to the 3x minus 12. And now we have an expression entirely in terms of x. And you could say that now we're done, in the sense that everything is now in terms of one variable. It's pretty much as simplified as it's going to get. But there's a couple things we can do. And if we do them, we'll actually find out that there is a really way more simple way. There is an exact value that we can write. So this involves a little bit of pattern recognition. In terms of, so in this numerator we have an 8, and in the denominator we have 2. And we also have these powers. So you know, in terms of powers and exponents, is there a relationship between 8 and 2?
8 is 2 to the 3.
Yeah. And if you didn't know that off the bat, what Gary means is if I do 2 cubed, that's the same as writing 2 times 2 times 2, which is 4 times 2 is 8. Even if you didn't know that, if you just divided 8 by 2, kind of naively, and got 4, you might notice that 4 is 2 and 2. And that would, on your own, you could work out that 2 times 2 times 2, 2 cubed, is 8. And here's what's interesting, is there's a 2 to the 3x. It isn't the same as 2 cubed, but it's visually similar enough that it's maybe a hint that there's like something you can do there with that. So if we rewrite that expression up above as 2 cubed to the x instead of 8 to the x over 2 to the 3x minus 12, one thing I might wonder is, can we get these parentheses here? See how over up top the 3 is inside the parentheses? I'm wondering if we can move these ones around. So now this is going to come down to being able to recognize and use some exponent manipulation rules. To start with, well, yesterday you were pointing out there's 2 ways you can do this. What was the way? Tell me what your initial way was.
To separate the 3x and negative 12 on the bottom.
So what Gary is getting at is that you can add and subtract powers of the same base. So generally, if you ever see, like, if you have a base a, the way they would write it in the textbook is if you had a to the b times a to the c, that would be the same as writing a to the b plus c. But that's a little bit confusing because it's letters, and letters aren't necessarily intuitive, but more intuitively, if we do 2 to the 1 times 2 to the 2, following the formula above, we would get 2 to the 3. But intuitively, we know that's true because 2 to the 1 is just 2, and 2 to the 2 is 4, and 2 times 4 is 8. So we can demonstrate that the formula holds, and if you ever forget the formula, you can kind of write out a simple example like that and show it to yourself. But it also goes the other way, because addition and subtraction are just going back and forth on a number line, and in some sense it's the same operation. It's just that one goes forward on the number line and the other goes backward on the number line. So it stands to reason that also the other part is multiplication and division similarly, in a different way, are not moving in steps, but they're jumping along a number line. So multiplication, division, sort of like opposites. but similar, addition, subtraction, opposites but similar. So we can conjecture that a to the b divided by a to the c is going to look like a to the b minus c. But because, yeah, and now we verify that that's true. So, and I'm actually gonna to keep the fractions nice, I'm gonna write it this way. I'm gonna let b be 2 this time. So, a 2 to the 2 divided by 2 to the 1 is the same as 2 to the 2 minus 1. See some parentheses there. So 2 to the 2 is 4 divided by 2 is, and what's 2 minus 1?
1.
So 2 to the 1 is 2. So 4 divided by 2 is, in fact, 2. So we can verify that it's true. But here's where things get fun. Because of that relationship between multiplication and subtraction being kind of interchangeable depending on the way you notate, we can actually put some parentheses around the negative and the c together, in the sense that we're separating it. It's going to be b plus negative c. And then according to our previous formula, we can split things out like this. A to the b times a to the negative c. Which is interesting. So a to the b divided by a to the c is the same as a to the b times a to the negative c. Now, why do we care? Because if we go back up, we're going to see that we have 3x minus 12. So we have one term minus another term, which means that we can separate this out like this. 2 to the 3 to the x over 2 to the 3x times 2 to the negative 12. Like that. Okay, so now what's our next step?
Simplify the top part.
Yeah, so the top looks a little bit complicated, and Gary's noticing that there's a way to make it look easier, which is, this is another rule that you can show yourself if you ever forget. But if we have an exponent outside of parentheses, we can bring it inside those parentheses by multiplying it by the inner exponent. So what that means is that we're going to get 2 to the 3x over 2 to the 3x times 2 to the negative 12. And so just quickly, sort of as we did down here, if I have a to the b parentheses to the c, what we're conjecturing is that that's the same as writing a to the bc. ACBC? ACBC? So again, let's plug in real numbers, as in we can do 2 to the 2 to the 3, and we're going to verify that that's the same as 2 to the 2 times 3.
Do you know what 2 to the 6 is off the top of your head?
Yes. Because,
64.
but there's an easy way of getting there.
Okay, yeah.
2 squared is what?
4.
Yeah, and 4 cubed is?
64.
We know that because it's 4 times 4 times 4. And grouping, 16, 4, 40, 24, 64. But up here, 2 to the 2, 3, 2 to the 6. There's a different way we can group, which is we could say, we know that well, here's where this gets fun. You can break things up and down and put them back together in different ways. 2 to the 6 is the same as 2 to the 2 times 2 to the 4, right? Because 2 plus 4 is 6. So 2 squared is 4, 2 to the 4, 16, 4 times 16 is what we found before, 64. So now we validated that this rule holds. So anyway, if you ever forget, just plug things in and work things out with real numbers. But anyway, going back up to the more abstract 2 to the 3x over 2 to the 3x, what can we do now?
There's two to the 3x's.
Yeah, so we have matching terms in the numerator. The 2 to the 3x and the 2 to the 3x, which means that they can cancel. So we literally just divide them out. And that leaves us with the value 1 over 2 to the negative 12. And we know something. Did we miss a step?
No.
But wasn't it?
2 to the negative 12. You can bring that up.
Yeah. But wasn't it negative 12 as the answer, or did we have it in exponent form?
Just 2 to the 12.
Yeah, okay. Yeah, that's right. Yeah. Okay, I'm second guessing things. But yeah, so what Gary is pointing out is that we have this negative exponent, and whenever you have, if you have an exponent, if you have an exponent in a numerator as negative, you can bring it down into the denominator. And if you have a negative exponent in the denominator, you can go across the line up into the numerator. So literally we just go boop with the whole term, and we get 2 to the 12 over 1. So just flip across the line. And 2 to the 12, if we really want to get fancy with it, is the same as 2 to the 6 squared, right? And we found that 2 to the 6 is 64. So 64 times 64 is going to be in the neighborhood of like 3096.
Wow. 64 times 2. 64 times 64. Yes.
Yeah.
Yeah.
And do I have that right? I have that wrong. Okay. It's going to be like 3600 roughly.
Yeah.
Because it's so the way you can estimate this kind of thing is if you drop the 4's and just make it 60 times 60, we know that 6 times 6 is 36. And we have the tens place in both, so we get 2 zeros, and we end up with 3600 is the approximate answer, and it's going to be a little bit bigger than that because of these 4's in the ones place. But for our purposes, if I were grading this, I would accept 2 to the 12 as an answer. But anyway, back to the beginning. It's surprising that we got an exact value. And most of the time, if you have one equation and 2 unknowns, you can't get an exact value. But this is a special case where, because of the relationship we were initially given, 3x minus y equals 12, when we plug that 3x into the 2 to the y, and we decompose the 8 to the x into a 2 to the 3x, we end up with this situation where we have this symmetry where 2 to the 3x is the same as 2 to the 3x, and then we end up basically just with that 12. And then 2 to the 12, which is not quite mathematically rigorous, but I just did there. But it's intuitive that this is true. And most of the time, if this equation had been set up any differently with different values, it wouldn't have been true, and we would have found a non-specific answer just in terms of x or y. So this is a fun problem because it does make you rack your brain a little bit. And it's also a good exercise in going through lots of exponentiation rules. And just to recap what those were, we had adding exponents, and we had multiplying exponents. Those are the primary ones. And we also had, when you have a negative exponent, you can flip the numerator across the denominator, and vice versa. So we had a to the b times a to the c, and we had a to the b to the c, and we had 1 over a to the negative b. And in these cases, a to the b times a to the c was what?
A to the b plus c.
And a to the b to the c is the same as?
A to the b times c.
Yep. And the last one?
Is just a to the b.
A to the b, yeah. So these three formulas, and they're related cousins because you can also do a to the b divided by a to the c, and you get b minus c. Are good to keep in mind because if you know them by heart, then if you see a problem like this with scary looking exponents, you can break it down quickly. So anything else?
I don't think so.
I don't think so. So across those two problems, we talked a bit about something that came up in both cases was recognizing situations where you need to define one variable in terms of another variable and substituting. So that's an important skill. Yeah, and then we talked a little bit about proportionality